Yeah, so thank you for the introduction. My name is Sanne. I work at CodeSandbox, it's an online IDE. Like it's VS Code in the browser, but hopefully better. So what I'm going to be talking about today is garbage collection. Doesn't sound very exciting, but it's quite useful to understand. So yeah, like said in my introduction, I used to be a teacher, so I don't have a formal computer science background. And, you learn a lot as you go, but I don't know, like things like memory management and garbage collection always seem kind of like magical to me. But in reality, it's just more algorithms, more computer stuff, basically. And yeah, and it's like in history, right? Magic is usually just science that you don't understand yet. And well, the point of this talk is to hopefully make garbage collection a little bit less magic. So first of all, we're going to have a look at some basics of garbage collection. And then the second half, we'll dive in specifically into how the Beam or Erlang and Elixir specifically handle garbage collection. All right, so you can think of your program, like if you first start your program, you can think of it as like a new house that you've just moved into, right? Everything's neat, you've got lots of space. But if you don't clean up, before you know it, your house looks like this. This is not quite a picture of my bookshelves, but it's close. And this is where garbage collectors come in. They keep track of your memory and make sure that your house, stays relatively tidy as opposed to messy. So garbage collectors have 3 jobs. First of all, they allocate memory. They tell you which shelf to put your stuff on, basically. And whenever I say stuff like stuff or objects or whatever, I just mean anything that can be created, right? An object, I don't mean that in like an object-oriented kind of way, just anything that needs to be stored. Its second job is to find what is the garbage, like, sort through all the stuff, figure out what can be thrown away and what you might still need. And then lastly, it needs to actually free that memory. Of these 3 things, the middle one, finding the garbage, is by far the most difficult part. Because if you don't clean up enough, you run out of memory, everything crashes. I'm sure you've had Stack Overflow errors or sometimes out of memory errors. Just the other day, we brought down by accident our entire staging server because we had a spike that went from 90 megabytes to 3 gigabytes of memory and everything crashed. So yeah, you don't want to be too careful in cleaning up. But you also don't want to be overzealous. Because if you clean up stuff that you're still using, you have a problem. Your program might expect something to exist that doesn't exist anymore. So there's different strategies to do all this. And we're going to have a look at a few of them. We're not going to go into like really the nitty-gritty implementation details, just the idea of how they work. So first of all, the most simple, straightforward way is called reference counting. The basic idea is if nothing points to it, nothing's using it, I can throw it in the garbage. So what we do, and this is all pseudocode, this isn't any real code. Let's say for everything that we store, we keep track of how many things reference that. You would almost have expected that because, it's called reference counting. So let's say we have a variable and we give it the value code-beam. So we put that string somewhere in memory. The garbage collector tells us where to put it, or the memory allocator. And it says, okay, one thing, the variable name is pointing to this. Now we make another variable, very creatively named other name, and point it to that same string. Now there's 2 things referencing the string code-beam. So far, it's not garbage because these two things could be using it. Now, if we set the first one to nil, the garbage collector or the reference counter knows, okay, name is no longer pointing at this. So now only one thing is pointing at it. If we do the same thing with other name, the number of references drops to 0. So now nothing is referencing this anymore. And a reference counting garbage collector will now know, okay, cool, nothing's pointing to this, I can get rid of it. And as you can imagine, this is fairly straightforward and fairly fast. Python, for example, uses reference counting for a part of their garbage collection. And as we'll see later, so does the Beam. But there's one big potential problem, and that's called cycles. And that happens if things are pointing at each other without a reference from the outside. So let's say I have this map. Excuse me. I have this map called A. So that has one reference now. It limits cubby, and one thing is pointing at it. Then I make a new map, B, and I point that at the first map. Now there's two things pointing at that first map. And then I do the same thing, pointing backwards. Again, in reality, this would be, much more complicated. Like the whole map would probably not be in like one spot in memory, but it's, to illustrate the principle. But what happens now if I empty A and B? What happens is the reference counter knows, okay, A is no longer pointing at this, cool. We count down by 1. B is no longer pointing at this, but so we count down by 1. Oh, I'm so sorry. But you can see the problem, right? These two things, they're still pointing at each other with no way from the outside to get to it anymore, to further drop it. So in a very simple reference counting algorithm, a thing like this would just stay forever. Because the reference counter would have no way to know that even though it's still 1, it is trash, even though it won't know. So a different way to do it could be mark and sweep. The idea behind that is if you can't get to it, you can't use it. So think of it like, that one thing all the way in the back of your kitchen drawer. It's so far back, you don't even know how to get to it. So you honestly might as well get rid of it. So to do this, you have all the objects in your program, and you start from the root. The root can be lots of things. It's usually anything that's on the stack currently being used, or any global variables, things like that. Things you know for sure are not trash. And then you follow any outgoing references from that, and you keep going and going and going until you have no more references, no more outgoing, links to other things. And then like all these boxes that are now gray, everything that you've seen, you mark as still alive or, useful. And then you know that everything else that you did not mark is trash. If you can't reach it, nothing's using it. And you can clean that up. And usually, by cleaning it up, the garbage collector doesn't actually go in and delete everything. It just says, okay, this memory can be used by something else. So it just it'll just give the spot away without explicitly deleting everything before. So this is nice, right? This will find cycles, because if we can't get to them, we delete them. A downside is that in simple versions, you have to stop your entire program. It's called a stop the world algorithm. There's smarter people have found fancier ways to do it that doesn't require stopping everything. But in the simplest way, you do, because, what would happen if something gets created related to something you've already checked? Then you don't know that even though it was just created, it's not garbage. Another downside is, as you can see, at the bottom, we free memory, but we end up with little gaps. And that's where copy and collection comes in. Copy and collection helps us keep our stuff together. So let's say we mark what isn't garbage, kind of the same way we did before with the mark and sweep or any other way. But instead of freeing whatever we didn't mark, we copy everything that we're still using. So we divide the memory into two parts, and everything that's still in use gets copied to the other space. As you can see, this has the benefit that everything gets kept together. So instead of little gaps in the memory, you always have the biggest possible chunk together available. The downside is that you, in practice, are only using half your memory at a time, right? Because when we're done, we just clear that whole top one, the from space, and we continue working with the to space, which becomes the new from space, and so on. We just keep going back and forth. So this is nice, but you have to use, you use only half your memory, so you do have to collect more often. So the last thing we can look at, oh, I went a little bit too fast there, is generational collection. Generational collection helps you, helps you look at only the things that are likely to be garbage. So there is it has been observed by many people who, looked at that kind of thing, that objects are likely to become garbage very quickly after they are created, or not for a long time. So something, either it's like, fire and forget, you use it and you immediately get rid of it, or it's something that you probably need. And so we can use that to our advantage. So similar to copying, we have two memory spaces. But in this case, we have new and old. So initially, everything gets created in the new space. It's all fresh, etc. That fills up. We garbage collect it, create some more things. And then at some point, everything that has survived, we keep track of how many garbage collection cycles an object has survived. And this can, sometimes it's one, sometimes it's two, or more. And any object that has survived a few generational collections gets now moved, gets promoted to the old object space. And that one we won't collect, or we won't collect nearly as often as the new space, because of that like that heuristic that if something lives for a while, it's likely to live for a long time. So the benefit is we're not checking everything all the time, right? The downside is that you cannot guarantee that you find all the garbage all the time, because the old stuff still can become garbage, and we're not checking it nearly as often. So this is a very, very quick overview of just like the general principles of garbage collection. There's more algorithms. All of these have variations in different like levels of like complexity, and like any language will have implemented a more advanced version of what I explained just now, but these are the underlying principles. So now the question is, what about the beam? And to prevent myself from coughing, I'm just going to take a quick sip of water before we move on. I'm sorry. Okay, hopefully that'll tide me over. So what about the beam? Well, you'll see that basically all these things that we just talked about will come back in one way or another. But there's two things, two big benefits compared to other languages that we have. The main one is isolated processes. That's really helpful because, a process, a short-lived process, if it dies, we can just get rid of everything it contained. We don't need to worry about it. And second of all, we have immutability. So stuff becomes garbage much quicker, but you also you know that like stuff probably won't be deleted out from under your feet because of immutability. So there's two different types of memory in the beam. Each process gets its own bit of memory. And when a process dies, that whole bit of memory just gets, freed and allocated to a new process. And then there's a shared bit called the binary heap, which we'll look at very briefly first. So this is called the binary heap, which, as you may have guessed, is where binaries go, specifically large binaries of more than 64 bytes. This is to reduce the overhead of passing these back and forth through processes. So the binary itself gets stored on the binary heap, and the processes store a pointer or a reference to where this binary lives on this shared heap. The binary heap uses reference counting. So every time a process runs garbage collection, and how they do that we'll go into in a second, but every time a process runs a garbage collection cycle, if that process did not say, okay, I'm still using this binary, marked that pointer as alive, the binary heap says, okay, that's one less reference. Do I have 0 references? Okay, cool. This binary is now garbage. And because it's only binaries, the problem with cycles that we talked about before can't occur here because these binaries, they can't point at each other. But the more interesting part, perhaps, is what happens inside a process. Well, for a very short-lived process, we probably don't have to collect, right? If it's just like a task and it calculates a few things and then it's done and returns its answer, that's cool. The whole process can be freed up in one go. But for bigger, longer processes, the memory is divided in two parts, a heap and a stack. And they grow from opposite ends to each other. The stack is where everything lives that you're currently using, like local variables, incoming, outgoing parameters. And the heap holds more like longer term permanent things, to put it simply. When they meet each other, we're out of memory, and we run garbage collection on the heap. Because again, everything in the stack is what you're currently using, so you know that you want to keep that. So step 1 is a copying algorithm. We already saw that, so we know how it works. So we start from the roots, which among other things is everything on the stack. And similarly to what we've seen before, we copy everything over. And to know when we're done, we keep track of the start and end of what we copied in each pass, which are the orange lines you see at the bottom, or you hopefully see at the bottom. And once these lines end up in the same spot, we know that we're done copying. And then the stack gets copied over as well. And this is always the first time we garbage collect. This is basically what happens. And if this happens and we don't free enough memory, the process can increase, can ask for more memory and grow so it can keep running. Another one that we're going to use, or that the beam uses, is generational collection. Like I said, they're all coming back. The beam uses basically all of these in one way or another. So let's imagine that this top row is what we have left after our first round of garbage collection. Because we've copied everything that was still alive over, we now, sorry, I lost my train of thought there for a second. We now know that everything that was created before this point has survived one pass of garbage collection, right? So we put a marker there in that spot that's called the high water mark. And we now know that everything before that has already survived a round of garbage collection. So everything that's created after is new. It's like the young, the baby generation. So now, I don't know why these are suddenly letters. I guess that makes it easier to tell the difference. So now everything that was created before is old, and everything that's created after is new. So when we run another round of garbage collection, everything before the high water mark, or below, I guess most people visualize it more vertically than horizontally like I did, but everything below or before the high water mark has survived one garbage collection, so we now consider it old. So as you can see, we move everything that already survived one over to the old space, and everything that was below the watermark, above the high watermark was new and gets moved to the to space. Then we put a new high watermark in the to space right after the C, as you can see on the slide, because now we know once again that everything before that is old, has survived one generation, and everything that will be created after is new. So by default, we don't collect the old heap at all, because the logic is this will live for a long time, and we'll just collect the whole thing when the process is done. But in some cases, you can manually trigger a full sweep if necessary, or in some cases, a full sweep will be done, in which case they'll just do the same as the first version, where everything that just gets treated as one and the same, as one and the same thing. And apparently I spoke 100 times faster than I did in my rehearsal. That must be the nerves, because garbage collection is hopefully no longer magic. And thank you for your time. I hope you have questions. I did not look at the chat while talking because that's too distracting. I'm sorry, I was apparently really fast. I timed myself before and it was a solid 30 minutes, but I guess that's just what happens.
This was excellent. Sanne, I mean, and there are some blog posts out there that try to describe this whole garbage collection process, but your presentation showing this step by step with your explanation, it was awesome. This was really great work.
Thank you so much. I'm still putting those teacher skills to use occasionally, I guess.
Oh, right. Your teacher's background played a role here.
Sometimes it's still useful.
Very, very good way to explain stuff here, and which is tricky, and it's not an easy thing to reason about. So we have a question here. First question is, did you ever face any production issues with your systems where you had to fine-tune the garbage collector settings, the default settings, or somehow work around its default behavior?
No, I have not actually. Oh gosh, I see myself twice. Wait, let me minimize this window or I will lose my mind. Yeah, there we go. That's better. No, like I said, I've never had to fine tune the garbage collection. And I think probably by far most cases, you can go through your entire career without ever having to. Yeah, like I said the other day, we did have to debug a big memory issue. But by the time I figured out what was wrong, it turned out it was a bug in Ecto that Jose had long before fixed, and we were just on an old version. So that wasn't as exciting for me to fix as I'd expected it to be. But that's really the only big weird memory issue that I've ever encountered. And turns out I didn't have to fix that.
I see. Okay, good. We have another question from Brandon. I will ask you to unmute if possible and ask the question yourself. Brandon?
Sure. Yeah, so I was wondering if there's any tools that allow you to introspect the current state of the garbage collector Ruby has something that does this called the GC module. So I was wondering if there's anything in the Beam that lets you easily do that.
I'm not actually sure, honestly. I don't know of it, but to be fair, I've also not really like looked for it. I used like the Erlang Observer, which tells you a little bit about what's going on memory usage wise, but it's not really like the garbage collector itself. If anybody else knows, I'd love it if you like put it in the chat, because I don't know of any, but they probably exist.
What one could use are trace events generated by the garbage collector. If you subscribe to this type of events, you will get some information from the garbage collector when it entered, when it is done, and how much memory was reclaimed. So such trace events could be used for some reasoning, but probably this is not exactly the kind of tooling that you had in mind, Brandon.
Right.
Okay, good. One technique that I have found in the past, which was useful when we were having some processes leaking memory, was also to hibernate a process. So when fine-tuning garbage collection, it sometimes might be just easier to hibernate a process every now and then, and such a process would then completely sort of remove and reclaim memory from its heap, and will just keep one frame on a stack. So this might be also a way to optimize memory issues.
Cool.
We have another question from Vasu. Let me see if we can ask Vasu to ask the question. Vasu, can you try to unmute? No, I'm going to read it out. For any reference to read more about this topic?
Yes. Oh yeah, I forgot that. Oh, there we go. One of the things, the main sources that I used are the garbage collection handbook, which really goes into garbage collection in general. Like, it's very technical, very mathematical. Like, you know, it explains the algorithms and all the pros and cons. And like, what I told is maybe like, I don't know, like the 5% baby steps of like the detail that this book goes into. Yeah, and I also used some information about the Erlang garbage collector, most notably a blog post by Lucas Larsson, and some other sources that I used more recently that I forgot to put in my slide. I'll look them up and I'll post them in the chat.
Excellent. Indeed.
Although don't find me in person later, because that would be weird if you're in my house.
There is the Q&A tab, and you can indeed answer all your questions in writing if you would like to, and follow up on some of those questions. So please do
awesome.
visit it,
yeah,
Sanne.
I see it. Cool.
We have next question from David. I will also try to ask him to unmute. David?
Hello?
Yep.
Hi.
Yeah, I was just thinking, like, isn't it dangerous to have this old space which you're never ever garbage collecting? Because I know that there are VMs running at Klarna for months and months, where you can potentially have a PID that's alive for a very, very long time. Doesn't that become a problem if there is like a small leak in the old space?
Oh no, I don't mean never. It's just like, usually it's not necessary to collect it again. But if I remember, let me think if I remember correctly. If basically the size, if there's not enough space at some point after sweeping, when there's too much stuff in the old heap, it does trigger a full sweep.
Okay.
So it gets triggered occasionally. It's just that most processes are fairly short-lived and it won't be necessary. But in like long-lived processes, it will be triggered occasionally, just not very often.
I think there's a counter. There's a counter of the minor sweeps, and after a certain number of such minor sweeps, we will get a full sweep.
Yeah, and you can also set that yourself if you want, if you feel like it needs to happen more often or less often.
By default,
also,
it's a high value.
Sorry?
By default, it's a high value indeed, so it may seem like forever, but you can set it to something lower.
Yeah, but it will eventually do it.